So let me do two examples here today. First, then we start part B, part C, part D, yeah. All right. The basic Laplace steps. So here we need to practice, get ourselves familiar with the basic formulas. When we use Laplace transforms to solve ODE, you can see the procedure is pretty much a standard. Yeah. So that means for almost all those questions, what we are doing basically the same. Yeah. Although the computation details could be different. Yeah, but the high level process pretty much the same. Yeah. So that's the reason most people like this method, Laplace transform method. But for us, after I introduced the Laplace transforms, but we still need to learn some other techniques. Yes. Yeah. Otherwise, some students may want to skip other techniques. Yeah. But we need to learn other techniques from the problem solving point of view. Okay. Yeah. All right. The first question, this simple second order ODE. So then we have the two initial conditions. Yeah. All right. So let's solve it. Yeah. And if we do not use Laplace transform, so you can see, so we need to find the general solution of the homogeneous equation. After that, so we add that t back. Now we find the general solution for the non-homogeneous version after, because we will have two unknown constant. Yeah. In the general solution, we will have two unknown constant. Yeah. So then we plug in two initial conditions, so we can find the values of those two unknown constant. Yeah. All right. Yeah. So here we just apply Laplace transform directly. Yeah. Both sides. Yeah. But before we apply Laplace transform, yeah, I like to give you the related basic formulas. Yeah. All right. Just for convenience. Yeah. The first two formulas, yeah, the derivative formulas. Yeah. First derivative, second derivative. Yeah, these two formulas. Yeah. All right. Then, yeah. So here, apply these two derivative formulas. You can easily, because the computation is not very hard. So I just write the equation directly. Yeah. Here actually, yeah, so you can see, yeah, so you may ask me why, right? Yeah. 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 Actually, there are some cancellation thing, I think. Yeah. Yeah. Why? Yeah. So, yeah, let me try a little bit here. Yeah. Yeah. All right. Yeah. So the L y double prime, yeah, based on the second formula, S squared capital Y. Okay. Yeah. Yeah. We use the L of little y, capital Y, minus S y0, that is S. Yeah. F prime, right, that is 1. Okay. Yeah. So here you can see we have this part. Yeah. So then, yeah, but the next one, next one. Probably we have some, yeah, next one, let's try. Y prime. Yeah. S times Y. Yeah. S times Y. Oh. Yeah. Minus F0, 1. Right? Oh. Then, yeah. This looks not quite right, right? Yeah. Looks not quite right. Yeah. Oh, that's why. Yeah. Yeah. So it should be minus S Y minus 1, right? Yes. All right. So then cancellation, yeah, right? So this should be S squared capital Y minus S Y minus S equals 1 over S squared. Yeah. LT is 1 over S squared. Remember so L of T, little t, is 1 over S squared by a basic formula. Yeah. So we will, we will update that. Yeah. These formulas may not be right. Yeah. So let me give you the LT. Yeah. Look at the LT. Our basic formula number 2. LT 1 over S squared. Yeah. All right. So we should get this one. Yeah. So that is S squared minus S times capital Y equals S plus 1 over S squared. Okay? All right. Then let me divide it by S, both sides first. S minus 1, Y equals 1 plus 1 over S cubed. Yeah. Then another division, Y equals 1 over S minus 1 plus 1 over S cubed, S minus 1. All right. So then, yeah, so it's different from our, my, yeah. Then L inverse equals 1 over minus 1 plus like that. Okay? Yeah. Then we apply formula. 1 over S minus A. See? Yeah. So that's easy, right? Yeah. A equals 1. Yeah. So the first term, e to the t. Yeah. Second term, yeah, a little hard. Okay? Second term a little hard. Yeah. Yeah. Second term. Yeah. Yeah, let me show you this way. Yeah. Yeah. So we need to represent. Yeah. So first, let's look at this fraction first. Yeah. Because this fraction, the structure is pretty simple. Can you see this one equals S1 minus S. You just do the common denominator, so then the numerator S minus parenthesis S minus 1. So you get the same thing. Yeah. If you can see this split like this, then we can write equals right? Yeah. But this one, yeah, so we just, we can still, we get from here S squared S squared, right? See? Yeah. We apply this formula, but we multiply 1 over S both sides. So we have 3 formulas. You see? 1, 2, 3 formulas. Alright? Can we add up these 3 formulas? Both sides adding up. Yeah. Because when we add up, this term cancel out. This term and this term cancel out, right? Yeah. So we will get, yeah, so let me clean up. We will get 1 over S minus 1 equals, yeah, these terms. 1 over S minus 1 minus 1 over S minus 1 over S squared minus 1 over S cubed. See? Yeah. After that, yeah, so then we have, yeah, let me write one more step. Yeah. So this last term, the second term, inverse Laplace 1 over S minus 1. Then minus inverse 1 over S1 minus inverse 1 over S2 minus inverse 1 over S3. How about that? Okay. And this one, the same as the first one, right? We just did one. We did one. Okay. So we will get 2 times e to the t. Then the next 3 terms, we need to apply a formula. Remember, we have a formula. Last time we learned the formula. Laplace transform of e to the t. Remember that formula? Equals n plus 1 factorial over s n plus 2, right? Remember? Yeah. Yeah. So last time we have this formula. Yeah. So that equals 1 oh t 1 oh yeah, it's not. Oh, sorry. Yeah. Yeah, because we need to use this one to check it. So then use this formula, check it, n factorial plus 1. Okay. Yeah. Yeah. I think we can see it. Yeah. So let me go to the previous slide to check it. Yeah. So first, let me get out. All right. Then move back to our basic formula slide. This one. Yeah. Yeah. So look at the here, yeah, n factorial. Yeah. See this one, n factorial over s to the m plus 1. Yeah. Formula number 4. Yeah, formula number 4. All right, so okay. Then this one, yeah, already pretty messy. Yeah. 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 Okay. Yeah, because that the previous calculation not right. Yeah. Here I just show you. Yeah. Yeah. The basic calculation steps. Yeah. Then the last 3 terms we can apply this formula. Okay. Yeah. The first one, n is 1, so 1 over s squared. 1 over s squared. The second one, n is 2, so 2 over s cubed, so, inverse, sorry. Oh, sorry. That's wrong. Just a minute. Sorry, yeah. Yeah, the first one, n equals 0. 1 equals 0 factorial, remember, that's 1. 1 over s. Yeah. Then that means inverse Laplace is 1. Okay, yeah. So this inverse, yeah, because we do inverse Laplace, not Laplace. So it's 1. Yeah. Then the second one, we do inverse, yeah, because the second one, LT equals 1 over s squared. So inverse 1 over s squared equals t. Okay, equals t. So minus t. Yeah. The next inverse Laplace transform. Then the third one, n equals 2. So Laplace t squared equals 2 over s cubed. So then inverse 1 over s cubed equals 1/2 t squared. Okay, so minus 1/2 t squared. All right, yeah. Here, just I do all the details here, yeah, because I want to show you step by step. Yeah. Yeah. Let you see everything here. Yeah. Although my old computation here not right. Yeah. I will update. I will update these equations. Yeah. But here I use hand calculating to correct it, to show you all the details here. Yeah. All right. Yeah. But you need to be very familiar with the basic formulas. Laplace, inverse Laplace. Yeah. Do not get confused. Yeah. When you do the calculation, be patient. Yeah. And slow down. Yeah. Yeah. So then carefully do the calculation step by step. Yeah. Expect your second homework assignment, so you need to do a lot of exercise questions on Laplace transforms. Yeah. All right, so that's the first example. Yeah. Second example, let's do another one. Yeah. Comparison with the usual method. Yeah. Usual method, yeah. The one I described at the beginning, yeah, that way. And here we will use Laplace transform. Yeah. Yeah. So this one I want to go a little fast. Yeah. This one, calculation should be correct. So I do not need to correct it. Yeah. Otherwise, too slow. Yeah. All right. So let's apply the Laplace transform. Yeah. Yeah. L of the y double prime. Yeah. So we can use these two formula after simplification. Yeah. So the first L double prime, so we get this one. Yeah. Oh, sorry. Yeah, because this is 0, so that term is gone, right? Yeah. So we only have two terms. So the first, we have two terms. Second, y0, yeah. Second, yeah. These two terms. Then 9y. Yeah. So this looks correct. Yeah. All right. So we factor out y, then we get an algebraic equation, so we can find the y formula easily. Then we need to break it in, we need to do the fraction decomposition. Yeah. Fraction decomposition, right? Yeah. You know, the numerator part, yeah, we write the numerator part first. Yeah. All right. So here the basic formula. Yeah, two basic formulas we need to use. Yeah. All right. Yeah. So the numerator, we do this kind of decomposition first. Oh, sorry, denominator. Sorry, denominator, we do this decomposition first. Yeah. Then the numerator, we do an adjustment. Yeah, because we want to, you know, have the same S structure. Yeah, shift structure. This is a shift structure. Yeah. The shift structure, okay? Yeah. Here. Yeah. All right. So then we can write inverse Laplace transform. Yeah. All right. Yeah. So the first part, yeah. First part, yeah. Constant can be factored out. The second constant, but we need to make this step. You know, yeah, because this is omega squared. This is omega squared. Okay, so we need the omega here. This is omega here. Okay, all right. Yeah. Then we need to make up something. Yeah, make up something. All right. Yeah. So then, you know, after simplification, so you can get that. Then, just the formula directly. Inverse Laplace transform directly, so you get the solution. Yeah, yeah. So this one you can see pretty straightforward. Yeah. So the solution, yeah, pretty straightforward. Yeah, yeah. But for comparison, yeah, so you may like to work using the old way. Use our previous method, so we can see if you can get the same solution. Yeah. So the old method, because it's a homogeneous equation, so you can write the general solution using the characteristic equation. So you can go back to our old formulas. So then, you know, you plug in initial conditions to see, yeah, if you can get the same solution. Yeah. All right, so that's the second example. Yeah. Although we have third example, yeah, yeah, but the third example, yeah, so there is one, yeah, important property here. Yeah, shifted data problem. One important property here. Yeah, so the question like this, I'll give you the question first. Yeah. All right, but the question here, there is one technical difficulty here. We need to get around or find a way to handle it. Yeah. So here, look at the two initial conditions. At the point pi over 4, it's not at 0. Okay. Yeah, we know initial condition can occur anywhere, right? Yeah, not necessarily 0. Yeah, but our main formula, derivative formula, our main derivative formula. Yeah, so here let me show you our main derivative formula. These two it uses the initial values at 0. If it's not at 0, then your initial condition cannot be used, right? Yeah, that's the technical difficulty. We need to, find a way, to, to change that. Yeah, change the. Here you can see, because we have to use this formula. But the question is, you need to use a function slightly different from y. Okay, yeah, y function. You have this technical problem. Can you define a new function that is slightly different from y? Yeah, that new function is slightly different from y. Yeah, but that new function, this initial condition, these two initial conditions occur at a 0 point, not at a pi over 4. At a pi over 4, we cannot use these two conditions. But we can introduce the new function, right? Yeah. So that's what we call it, the reason shifted data, because we need to shift the variable of y, in an appropriate way. Okay, all right, yeah. Here, this example, because relatively hard to understand. Yeah, and today I already spent a lot of time in the previous two examples, so I want to leave this relatively hard example next time. Yeah, next time at the beginning, I explain this shifted data problem. Okay, yeah. So now I just jump to part D for a new topic. Yeah, yeah. All right. Part D. Yeah, a new topic. All right, good. Part D, modeling of free oscillations and forced oscillations. Yeah. In this part, you can see, so we need to solve some application problems. Yeah, yeah. So after we know how to solve the second order ODEs. Yeah, so then let's apply our technique. Yeah, and in this part, for the solution, I didn't use the Laplace transform. Yeah. Although we can use, after we learn, we can use. Yeah, but the solution of part D, I didn't use Laplace transform. Yeah, so we can practice non-Laplace transform solutions. Here, D.1, mechanical mass spring system. Yeah. The system is very simple. Yeah. Okay, yeah. Look at the figure here. Okay, the figure. Yeah. So that's the system. Yeah. So we start with a spring first. Yeah. Okay. Yeah. Just a spring. Yeah. So after that, you attach a ball, okay? Yeah, iron ball, just some heavy ball, yeah, there. So the spring is stretched, yeah. All right, then. So this is the balance position, yeah. But after that, so you want to pull or press, yeah. Yeah, easier to pull, yeah, but a little hard to press it, yeah, yeah, in this position. Yeah. All right, so you can see, yeah, when you stretch it, stretch it with y displacement, yeah, y displacement, with respect to the, zero position, y equals 0. This is the 0 position. Okay? So you stretch it to y displacement. So then there is a force. Pull it back. Yeah. So in this system, how we study this system, yeah, the motion, yeah, because the position of the ball, yeah. So because we want to study the position of this ball as a function of t. Yeah, what is that function? Yeah. All right. So that system. Okay. So the spring, then restoring force. There is a physical law, Hooke's law. Yeah. Here we use the Hooke's law. Yeah. I think you learned in your middle school, yeah, Hooke's law, yeah, physics. Yeah. F1 equals negative ky. Yeah. K some constant. Yeah. K some positive constant. Yeah. F1. Yeah. The restoring force. F1 is the restoring force. Yeah. All right. And K, spring constant. It's a positive number. Yeah. This negative sign you will see because the force has a direction, right? Yeah. The force always has a direction. Yeah. And the displacement y function also has a direction, right? Yeah. So here, this negative sign tells us, the direction of the force F1 is always opposite the direction of y displacement. Yeah. That meaning, yeah. Then it's natural, right? Yeah, restoring. Yeah. So the opposite direction. Yeah. All right. The stiffer the spring, the property, the larger the K. Yeah. That's the basic property. Okay. All right. Yeah. Here we use this axis. This is the positive direction. Okay. Use this arrow, the positive direction of y. Yeah. Yeah. Going down. Yeah. So when y move down, so the ball moving down that direction, we treat as the positive direction. Yeah. Then F pulling back, yeah, upward, yeah, upward, that's the negative direction. Yeah. All right. In this system. Yeah. All right. Yeah. So based on that understanding, now we need to consider, setting up the differential equation on the system. Yeah. Force from the weight of the ball, yeah, because the ball has some weight. Yeah. That weight, by the gravity of the earth, so we have a formula. Yeah, that force. Yeah, that force we use F0. F0, yeah, equals by Newton's law, right? Yeah, or by it's the mass m, the mass, and g, the gravity constant. Yeah, yeah, and here, why it's force here? Yeah, F0. Yeah, F0. Yeah, right. Yeah, so yeah, yeah, the direction. Yeah, mg. Yeah. All right. So the weight. Yeah. Yeah. All right. Yeah. So. All right. The constant gravity, we use this unit. Okay. M over s squared. There is another one, feet, right? Yeah, feet. Yeah, here we use meter. Yeah. meter system, meter, second, kilogram, that system, yeah, metric system, yeah. So F0 has, yeah, although F0 follows this formula, but when we look at the whole system, F0 has no effect on the motion because it is in equilibrium with the weight W of the ball. Yeah. So you can see in the whole system, yeah, that in any position of the ball, the F0 keeps the same, right? Yeah, from beginning to end. It's a constant. Yeah. F0 is always a constant. Yeah. But after the system is balanced, then you can ignore the F0. Yeah. Yeah. Because, there is no change in the system on the F0. So the changing part is only F1 part. Yeah. F0 never changes. Yeah. So for that reason, we do not consider F0. Yeah. All right. Then Newton's second law, yeah, the motion. Now we need to study the motion. Yeah. The Newton's second law, mass times acceleration. So that's m times y double prime equals force. Yeah. So we have two equations. Yeah. Force, yeah. F1, force. Yeah. All right. So the force is the resultant of all the forces acting on the ball. Yeah. But here we do not, although it's all the forces, but we do not consider F0 here, right? Yeah. Yeah, but here, F0, yeah. So do we consider, yeah. All right, all the forces. Yeah. All right, so here, undamped system. Yeah. So here, conditions for undamped system. Yeah. All right. Yeah, so the damping is small. Yeah. So we understand this undamped system. Yeah. So when the damping is small, yeah, so we treat it as an approximation of undamped system. So the motion of the system is considered over a relatively short time, short period of time. Then we have a good approximation. Yeah. Otherwise, yeah, because, so think about that you may have many other factors, right? The air, so a lot of things, yeah, that may cause the problem. But under these two conditions, we get approximate undamped system. Approximate, yeah. So we do approximation here. Yeah. Yeah. If these two conditions are not satisfied, then our approximation is not good. Yeah. So here we make this assumption. Yeah. All right. By Newton's second law and Hooke's law, so then we have the equation, right? Yeah. So yeah. So you can see, yeah. M y double prime equals, yeah, that F1, right? Yeah. Equals negative ky. Yeah. So then you move this term to the left-hand side. So you get a very simple second order linear ODE with homogeneous linear ODE with constant coefficients. Yeah. So that's the type of equation we have here. Yeah. Okay. Yeah, very simple. Then we need to solve it. Okay. Yeah. It's very easy to solve it. Yeah. Characteristic equation, right? Yeah. The standard form. Yeah. Yeah. The way to solve, yeah, standard with constant coefficient a, little b, both constant. Yeah. So we use the, so what's that? Discriminant, right? Yeah, the concept, yeah. Quadratic formula, so there is a discriminant concept. Yeah. So, yeah. Here we simplify the standard form. Yeah. Yeah. A equals 0, B equals K over M here. Yeah. That discriminant concept. Yeah. So we know discriminant A squared minus 4B, but here the discriminant is negative. That means the characteristic equation has two complex solutions. Yeah, I, right? Then we need to use sine, cosine. Okay, all right. Yeah. So the y1 is this form. Yeah. All right. Yeah. 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 y2, that form. Okay. Yeah. So the omega. Yeah. Omega, we know this is omega squared. Okay. This is omega squared. Okay. All right. All right. Yeah. Omega 0. Yeah. Yeah. Here we use the notation omega 0. Yeah. 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 Because this constant has a special meaning. Yeah. So here we use a special notation omega 0. Yeah. Yeah. All right. So then the general solution, yeah, y1, y2 linear combination of y1, y2, right? Yeah. C1 times y1, C2 times y2, linear combination. Yeah. 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 Here the constant we use capital A, capital B. Okay. Although not a C, capital A, capital B. So linear combination of these two. Yeah. Yeah. Because here this term is gone. Okay. Why this term is gone? Because this A is 0, right? Yeah. AX over 2, that's 0. Yeah. So this E function equals 1. Yeah. So then in this solution, you do not see the E part. Yeah. Yeah. Because this A equals 0. Yeah. Yeah. All right. So that's the general solution. Yeah. Then to find constant capital A, capital B, so you need initial conditions. Two initial conditions, so you can determine capital A, capital B. Yeah. All right. So that's the, this. After that, then we study, yeah, because for the application problem, so we need to study some important factors. Yeah. Here, the period, yeah, the period concept, yeah, because it's a periodic function. Yeah. So this solution is a periodic function. So we want to look at its period. Okay. Yeah. The period 2 pi over omega 0. So why is that? Yeah, here we see it from the 2 pi periodic property of cosine function. So this cosine function, when you add 2 pi, it has the same value. Then you factor out omega 0. So inside the parenthesis, it becomes t plus 2 pi over omega 0. Then by the definition of periodic function, so this is the period, okay? By the definition of the periodic function. So remember I wrote the before, when we define periodic function, some period, capital T, equals that. But we needed this T, the minimum, smallest such T, okay? Yeah. Otherwise, any multiple of that T can be treated as a period. Yeah. But here we want the smallest period. Yeah. So this is the smallest period. Okay. But after we get a period quantity, next one another important concept we need to use when we study a system like this. That's the frequency concept. Okay, the frequency concept equals reciprocal of the period. Yeah, that's the definition of frequency. Okay, the relation between period and frequency, so they are reciprocal each other. Yeah. So the frequency, so that's omega 0 over 2 pi, the frequency. Yeah. Because this frequency concept in this system, it is important. Yeah. So here we have its formula, the frequency formula. All right. Yeah. And this frequency we give a name called a natural frequency of the system. Natural frequency of the system. Yes. Yeah. Yeah. The system has its natural frequency. Yeah. Yeah. And later, you will see later when we solve, some other similar systems, we may get different frequencies. Yeah. That's different from this natural frequency. Okay. So natural frequency never changes. Yeah. But when we solve other similar related systems, so our frequency could change, based on the data given in the system, so there are, some different frequencies of the solution, different frequency of the solution. Then we compare the solution frequency with the natural frequency. Yeah. So here we have this concept, natural frequency of the system. Yeah. All right. Yeah. Yeah, let me see. Yeah, we still have a few minutes. Okay. Yeah, next one. ODE of the damped system. Yeah. So we modify the previous undamped. So now we add, some new term to get this damped system. Yeah. All right. So this time you can see, there is some new component added into the system, that dashboard. Yeah. So you will see some force, right? Some stopping force. Yeah. Some force added to the system. Yeah. To slow down the ball. Okay. Yeah. All right. Add a damping force. Yeah. F2. Yeah. So here you can see F0, F1, F2. Each F has a different meaning. So here, the F2 notation we use to represent the damping force. Yeah. Yeah. The damping force equals negative C constant, some, damping constant, C, times Y prime, the velocity of the ball. Yeah. Y prime. Okay. Yeah. So, all right. Yeah. Here we assume that this damping force to be proportional to the velocity. Yeah. Yeah. It's a good approximation for small velocities. Yeah. So this formula, when the velocity is small, relatively small, by experiments, it's a good approximation. Okay, yeah. So although it may not be, very accurate, but it's a good approximation. Yeah. All right. So then we need to modify our undamped system. Yeah. The previous undamped system, we need to add this F2 into the equation. Yeah. So now ODE of the damped mass spring system. Yeah. So then you need to add this term. Okay. Yeah. The force right hand side. Yeah. But the force at the right hand side, it is negative, right? Yeah. So after you move to the left hand side, so you get a positive. Yeah. plus positive constant C times y prime. Yeah. So you get this. Also, second order ODE, but the coefficient of y prime is non-zero. That's the damped system. Yeah. All right. Yeah. Let me keep an eye on the clock. I still have a few minutes, 4 minutes before our break time. Yeah. So let me try to complete this slide before the break. Okay. All right. Then we try to solve it. Yeah. So this time, yeah, I mean, pretty straightforward. Yeah. The characteristic equation. So the standard form. Yeah. Then we get its corresponding characteristic equation. Yeah. With lambda as the variable here. Yeah. All right. So then discriminant. Yeah. This time we need to, consider this discriminant. It could be positive, could be negative, could be zero, right? Yeah. Yeah. So the discriminant, yeah, get this expression. Yeah. All right. Then case 1, the discriminant is positive. Yeah. Then we call it over damping the system. Yeah. We call it the over damping system. All right. Yeah. So the over damping system. Yeah. So we use alpha beta constant. Yeah. So we can write its solution. Yeah. Yeah. Because if you do not introduce new notation alpha beta, then the formula is too long, right? Yeah. So in order to make the formula as simple as possible, then we introduce the alpha beta constant. Yeah. That's the overdamping solution for the overdamping system. Case 2 equals 0, then critical damping system. Okay, critical damping system. All right. Then the solution C1 plus C2T. Yeah. Remember, so our solving characteristic equation, we have that T before. Yeah. We talk about that. Yeah. How to get it? Remember, so we have a special way. Yeah. If we know one solution, then we can find a second solution. Yeah. So that's the reason. So we can get this T. Yeah. Case 3, less than 0, under damping system. Under damping sine cosine, right? Yeah. Sine cosine, but we need some special constant, sine cosine. Yeah. Omega star. So you need to define your omega star. Yeah. All right. So in this way, yeah, so we can solve any such damped system. Yeah. Yeah. All right. So it looks pretty straightforward. Yeah. Yeah. We just apply, our solution solving second order homogeneous linear homogeneous ODE with constant coefficients. Yeah. We just apply our old solutions here, so we can solve, these two systems, undamped and damped. These two systems. Yeah. All right. So let me stop right here. Let's take a 10-minute break. Then we go to the second half.